My name is Ivan.
And my name is Yulong.
So we're from Bloomberg, and we'll be talking about fine-tuning Airflow, parameters you may not know about. So the agenda today will consist of the following. We will briefly introduce Bloomberg, our team, and how we use Airflow. We will dive deeper into what Airflow configurations are and showcase 4 case studies of production issues that configurations have helped us resolve. And lastly, we will summarize the key insights and takeaways. So let's start with a brief introduction of Bloomberg. So Bloomberg is a financial technology company founded over 40 years ago. Our main product is the Bloomberg Terminal, which is a software that delivers a diverse array of information, news, and analytics to more than 350,000 subscribers in 170 countries. The terminal is a huge real-time information aggregator that lets our subscribers take action related to their business and investment decisions. So we're both from the Data Platform Engineering department, whose goal is to provide an integrated portfolio of technology products and tools that enables content owners and application teams to perform ETL on business and financial data. So within the department, we use various technologies, including SQL, Spark, Kafka, Redis, and crucially, Airflow. So our team specializes in using Airflow to manage and orchestrate data workflows for global financial professionals. These professionals use our system to ingest alternative data, which are non-traditional data sources that go beyond the standard financial statements, such as pharmaceutical drug pricing and sales, or airline flight totals and jet fuel consumption, and more. So we transform click and drag no-code configurations that these internal professionals configure on the Bloomberg Terminal into data pipelines in Airflow, leveraging Airflow's dynamic DAG feature to generate DAG definitions at runtime. So once that data is ingested into our system, it can then be seen on various graphs and dashboards on the Bloomberg Terminal. So here you can see the previously mentioned pharmaceutical and airline flight forecast data in action. So clients will basically use this information to make decisions on their portfolio allocations. So the focus of our talk today will be revolving around Airflow configurations. So as a recap, Airflow configurations are parameters that control how Airflow behaves. They govern things like DAG parsing, scheduler heartbeat, database interactions, task queuing and retries, metadata cleanup, observability, and more. So when you first set up Airflow, one of the first steps is generating a configuration file that contains default values that Airflow provides out the box. This is enough to get a basic Airflow instance running, but as you scale your Airflow, you would inevitably need to customize these variables to configure things like advanced logging configuration, choosing the right worker executor, number of parallel processes to run, etc. And these configurations are often defined in a configuration file, as well as environment variables. And each of them has an order of precedence. So now, with a quick recap of Airflow configurations in mind, we will talk about how tweaking configurations can help resolve 4 different production issues that we faced on the team. So we will first present examples of issues that were largely based on our Airflow environment on our team that handles the ingestion of alternative data, given its unique challenges, and show you basically how we were able to use configurations to mitigate these issues.
All right, so the first issue we're going to talk about today is dynamic DAGs not parsed. One of the unique challenges that our team faces is managing over 2,500 dynamic DAGs, each corresponding to a distinct data pipeline. Now, you might be wondering, why do we need to dynamically create thousands of DAGs? The reason for that was because while these DAGs share many similarities, they also differ slightly based on different configurations. Each dataset comes with its own combinations of parameters, and those parameters varies for each dataset. By generating these DAGs dynamically, we avoid having to create nearly identical DAGs manually with the same task, but only minor variations. So in the next slide, I'll walk you through how we actually generate all those dynamic DAGs and why this approach eventually created our first issue and how we use the configurations to solve the issue. So we used to have a single file called create dynamic DAGs that generated all the dynamic DAGs at runtime. On the right, you can see a visual representation of one of the example DAGs with its various operators and dependencies. The create dynamic DAG file worked by calling internal service to retrieve a list of tables in our system, then obtain the tree of task descendants. Using this information, it constructs a dynamic DAGs. But some of the larger, more complex DAGs can include over 150 tags, making the process relatively resources intensive and time consuming. And here's where the issue comes in. As we began scaling up the number of DAGs in the system, we suddenly encountered an issue where none of the DAGs were being parsed and could not be found. The Airflow 3 UI in the screenshot here showed the message no DAGs found. So at that point, we turned to the logs to investigate the root cause. We examined both the DAG processor's processing statistics and the logs for specific files being parsed. So one detail immediately stood up. The number 50 kept recurring in the telemetry. The processing stats show that the last run of the create dynamic DAG took just over 50 seconds. And the logs indicated the processor of a DAG file was being killed after exactly 50 seconds. So it became clear to us that some configurations from somewhere was enforcing this 50 seconds limit. After some investigations, we discovered this DAG file processor timeout configuration under the DAG processor section. The default value was set to 50, the exact number that we had observed earlier. This number in general is sufficient for most cases, but in our cases, as we mentioned earlier, we used to create dynamic DAG to dynamically generate over 2,500 DAGs. So this limit might not be sufficient for our case. The description also confirmed our suspicion. This parameter controls how long a DAG file processor runs before timing out. So with that, we had likely identified the root cause. The next step was to experiment with adjusting this value. And here's what we did. Locally, we set it to a high number, 500, just to test to see if that will resolve our issue. From the DAG processor stacks this time, we observe a successful run for parsing our DAG file. The reported duration was 78 seconds, longer than the previous 50 seconds, but it's still well below the new 500 seconds limit. And on the Airflow UI, all 2,964 DAGs were now displayed correctly. So this confirmed that adjusting the DAG file processor timeout was the solution, and it helped solve our first issue. So a couple of key points here. So increasing the DAG file processor timeout to 500 allowed us to do a couple of things. First, it gave us a quick fix for the issue. Second, it allowed us to later on lower the values to a more appropriate level, as the 500 was just for debugging purpose. And finally, it bought us some time to think about longer-term solutions, things like cleaning up unused data sets, maybe splitting up the dynamic DAG generation into multiple files, or dedicating more compute resources to the DAG processor. So as you can see here, a simple configuration change could bring us a big operational win. Now let's take a look at the second issue, DAG parsing delay. And here's the issue. Whenever changes were made to the DAG files, it always took several minutes for those updates to propagate. Previously, we mentioned about the create dynamic DAG file, but on top of that, we also had dozens of static DAGs that were also processed during every DAG processing interval. And as you can see here from the screenshot, each file could take anywhere from 1/10 of a second to nearly 2 seconds to pause. So the question that we needed to answer was, how can we get the DAG processor to finish parsing all these files more quickly during each iteration? And this led us to the parsing processes variable under the DAG processor section. So this variable controls how many processes run in parallel to parse the DAGs. After experimenting with different values of this variable, we eventually settled on a configuration that worked best for our environment. And the result was it significantly improved the per iteration processing speed. So now that we managed to have each DAG processing cycle run faster and within an acceptable time frame, our next goal was to have the DAG processor parse the file more frequently. And this brought us to the mean file process interval variable, also under the DAG processor section. This variable defines the number of seconds after which a DAG file is reparsed. By default, it's set to 30 seconds, which is generally sufficient for most use cases. We experimented with different values, keeping in mind the trade-off that lowering the interval helps increase the refresh frequency, but it also raises the CPU usage. After some testings, we were eventually able to find the right balance between the update frequency and the resources consumption. As you can see, tweaking the parsing processes and mean file process interval allow us to achieve a faster DAG processing in each iteration and run the DAG processor more frequently, giving us updates to DAG structures that are as close to real time as possible. And the best part, none of this requires any code change. It was all done by adjusting the configuration variables. And throughout this process, we were very careful to account for the CPU usage trade-off when tuning these values. Some of the systems requires very frequent updates and can allocate more resources to achieve that, while some others may prioritize efficiency.
Okay. The next case study is the scheduler memory leak. So this case study is based on an issue that we encountered on the team. But in this case study, we've created an example with increased severity of the memory leak to help highlight the power of configurations. So memory leak was noticed in the scheduler. So the Airflow scheduler monitors all tasks and DAGs, and then triggers the tasks instances based on the scheduled time or dependencies completing. Think of it as the brains of the Airflow system. The scheduler was using an increasing amount of memory, which was causing it to get killed and restarted. This is an issue, as without the scheduler, no new DAG and tasks can run. And we looked at the memory consumption data of the scheduler process and noticed a linear growth in the memory, even in the first 5 minutes of its startup. So to find the root cause, we spun up a locally running Airflow instance and ran the above command. So this uses the Linux ps command to inspect the RSS, or the resident set size of the scheduler, running inside of a Docker container. And as you can see, the number kept increasing. Now, although this is useful to understand that the total memory consumption has gone up, there wasn't an easy way to figure out what specific process was causing the memory leak. So that is until we encountered the enable trace malloc configuration under the scheduler section. It's a useful feature introduced in Airflow 3, where upon setting this configuration to true and the scheduler process receiving the sig user1 signal, it will start tracing memory allocations and log the top 10 memory usages at the log level. Sorry, at the error level. As mentioned in the description, this is an expensive operation and should only be used for debugging purposes. And once the root issue is identified, it should be cleaned up. So once we enabled enable trace malloc, we sent a SIG user1 signal to the scheduler using the above command and saw the top 10 memory usages logged in the scheduler Docker container. And as you can see, there's a plugin renamed to Leaky plugin for demonstration purposes, which was consuming the most amount of memory when the processor starts. And this really allowed us to pinpoint the exact memory violator rather than just seeing the total memory go up. So once we identified Leaky plugin to be the issue, we removed it temporarily and looked at the trace malloc report after and saw that the Leaky plugin was no longer showing up as the top memory user of the scheduler process. And rerunning the earlier command of inspecting the scheduler process's memory usage after removed Leaky plugin also shows that the total RSS being very stable and is no longer increasing with time. And this demonstrates how, again, without introducing any new code, we were able to leverage built-in configurations to debug an issue within the Airflow environment. And the last case study that we will introduce is observability. So with many components running, we want to make sure that we have observability into the various Airflow components. With the previously mentioned problems encountered, namely no DAGs parsed and high DAG parsing runtimes, we want to make sure that if these issues occur again, we can identify them as soon as possible in our production environment. And we also want to have an overview of the system health by looking at the health of the scheduler, DAG run, Celery, etc. And the way we've achieved that is by leveraging statsd within Airflow. So statsd is a network daemon used for collecting and aggregating application metrics, and its standardized format is supported by various backends, including the ones that we have in Bloomberg. So we enable sending metrics to statsd by installing the pip dependency and turning statsd on to true. We then specified the metrics of interest in the metrics allow list under the metrics section of the Airflow configurations. So metrics allow list allows us to fine-tune to capture only the most useful metrics and leave the other metrics out as to avoid an overload of metrics ingestions. So metrics have been useful for automated alerting and ticket creation. So here we've included all of the DAG processing and DAG run metrics. And some examples that we've included are DAG processing.lastRun.seconds ago, which tracks the number of seconds since the last DAG processing run. And we use this to alert if it's been too long since the last run, indicating an issue with a DAG processor. We also track DAG processing.lastDuration to make sure that the DAG processing isn't taking too long and allows us to take actionable steps like splitting large files into smaller ones. And lastly, dagrun.dagid.firstTaskSchedulingDelay. And this alerts if there is a large delay for first task runs for specific DAGs of interest. And once again, we were able to change very little to our Airflow configurations and get a big win to observability.
Right, so overall, we hope that during the sessions, we have demonstrated how small tweaks to Airflow configurations can achieve big impact on scale, scalability, and observability. We also hope that configurations that we have demonstrated can also help you to solve some of the issues in your Airflow environment. Things to remember is always test with different values of the configurations in lower environments to find the right balance between the trade-off where applicable, and that temporarily changing configs can buy you time to look into longer-term solutions. And as you have seen earlier, there are configurations that have only been introduced in Airflow 3. For example, the enable trace malloc. So make sure to read the documentations and keep up to date with the latest configurations. And that brings us to the end of the presentations.